You know, some of the most powerful ideas in math, things like negative numbers or even zero, they all seemed impossible at first. They were just these abstract concepts, right? Until, that is, we found a way to actually visualize them. So today, we're going to dive into another one of those impossible ideas, one that unlocked a whole new world of geometry and technology. Okay, so how do you actually picture a number that isn't supposed to be real, like the square root of -1? If all the numbers we know and love live on a straight line, where on earth does this imaginary number, I, fit in? That's the big question we're going to tackle. So let me introduce you to the main character of our story, the complex number. It looks like a single number, but it's really made of two distinct parts. You've got the real part, A, which is a number we're all used to, and then you've got the imaginary part, BI, where that I is our square root of -1. Put them together, and you get this new kind of beast, A plus BI. Now, for centuries, this was a huge problem. Mathematicians knew you could lay out all the numbers on a single line, right? Zeros in the middle, positives go right, negatives go left. Simple. But this I thing, well, it just didn't belong anywhere on that line. So what do you do when one dimension just isn't enough? Well, the solution was brilliant in its simplicity. You add another dimension. And this was the amazing insight from a guy named Jean-Robert Argand. He realized that if these imaginary numbers don't fit on the line, maybe, just maybe, they live on a plane. So what you're seeing here is that massive leap from one dimension to two. On the left, there's our familiar number line. It can only handle real numbers. But on the right, the Argand diagram opens up this whole two-dimensional space. The horizontal axis, that's our old friend, the real number line. And that new vertical axis, that's where our imaginary number, I, finally finds a home. And what's really cool is that plotting one of these numbers is actually super simple. You just treat it like a set of coordinates on a map. For a number like A plus BI, you go A units along the horizontal real axis, and then B units up or down the vertical imaginary axis. The spot where you land, the point A, comma B, well, that's your complex number. And boom, here's what it looks like in action. All of a sudden, these totally abstract things have a real concrete place to live. The number 1 plus 2i is just hanging out at the point 1, 2. The number -2 plus I is over at -2, 1. Every single complex number has its own unique spot on this plane. The impossible has been mapped. Okay, but here's the thing. The Argand diagram is so much more than just a way to plot points. It actually reveals a hidden geometry baked right into these numbers, turning all that abstract algebra into something you can actually see and play with. Now this is a really crucial shift in how you think about it. That dot on the map isn't just a static point. Think of it as a vector, an arrow pointing from the center of the map, the origin, right out to that dot. And of course, every vector has two key things going for it, a length and a direction. And in the world of complex numbers, these two properties get their own special names. The length of that vector, how far it is from the origin, we call that the modulus. And its direction, the angle it makes with that positive real axis, is called the argument. With just those two values, we have a whole new, totally geometric way to describe any complex number. So here, you can see the two ways of looking at it side by side. On the left, you've got the standard way. Go x units over and y units up. That's great for things like adding and subtracting. But on the right, you have the geometric view, a vector with a certain length, r, at a certain angle, theta. And as we're about to find out, this is where the real magic happens, especially when you start multiplying. All right, you've got to see this, because this is probably the most powerful, most mind-blowing insight the Argand diagram gives us. What happens when you multiply two complex numbers? Well, if you do the algebra, it's kind of messy, but when you look at it geometrically, it's beautiful. I mean, just look at this formula. If you multiply A plus BI by C plus DI, you get this thing, AC minus BD plus AD plus BCI. Sure, it's correct, but it tells you absolutely nothing about what's really going on. It's just pushing symbols around. Okay, now forget that messy algebra for a second and just look at the geometry. It's this simple. When you multiply two complex numbers, you multiply their lengths and you add their angles. That's it. All that complicated algebra just boils down to a simple stretch and a turn on the plane. I mean, how cool is that? This move is so elegant, so beautiful, it actually has its own name, a spiral dilation. It's a combination of scaling the point further out or pulling it closer in and then rotating it around the origin. This is the hidden dance of complex multiplication. So really, the big takeaway here is this total shift in perspective. The Argand diagram takes a tedious algebraic chore and turns it into this graceful geometric dance. And this idea, a number that can rotate, turns out to be one of the most fundamental concepts in our modern world. So let's bring this back to the real world, because this isn't just some abstract math idea. It is literally the engine behind countless technologies we use every single day. I mean, seriously, think about anything that involves waves or rotations. In electrical engineering, the alternating current in your walls is perfectly described by a rotating vector on the complex plane. In signal processing, your phone uses something called the Fourier transform, which is all about complex numbers, to make sense of radio waves. The control systems in robots and airplanes use them to handle rotation smoothly. Heck, even at the tiniest scales, quantum mechanics uses complex numbers to describe particles. All of these fields depend on this one simple geometric idea, a number that knows how to rotate. So, when you step back and look at the big picture, the Argand diagram wasn't just a graph. It was a whole new lens to see the world through. It let us turn incredibly complicated algebra problems into intuitive geometric ones we could actually wrap our heads around. Which brings us to this fantastic quote from the mathematician Jacques Hegemard. He said, "The shortest path between two real truths often passes by a complex domain." It's like, by taking a detour through this imaginary world, we found a powerful shortcut to solving very, very real problems. It really makes you wonder, doesn't it? What other huge, seemingly impossible ideas are out there right now, just waiting for that one simple picture, that one brilliant diagram that's finally going to make it all just click?